Hello, y'all. Darrell Lee Berry Jr. here, back for some more physics. So we'll go ahead and do some reading tonight. We started a new topic today in class, in my classical mechanics class, graduate level. Some scattering due to a force field. So still don't know exactly how I did on the exam yet because we haven't gotten the scores back yet, but it will be graded soon. But I hope I did well, but sure I didn't do perfect. So I'll try to do better on the next exam. So that's what we're working on now. So what I'll do, the plan, is to get through this section of the textbook and see if I can help make that happen. And I may actually have time to do some undergraduate physics as well. We started a new topic in my foundations class as well. We started some EM, which those who've been watching for a while, you know I'm familiar with. I actually was a learning assistant in mechanics for a while. Excuse me, on EM for a while. So, of course, there's some details I forgot to be refreshed on. I think for the most part, I'll do okay on that section of the foundations, but we'll see. So, starting momentarily, have the book up, have the tablet up, and I will get through this section, so hold on to your seats. I don't know how long it'll be, but there we go. And maybe make it a little smaller. There we go. So this is what we're looking at, still in chapter 3 of Gold's Mechanics, graduate level, scattering in a central force field, and pretty sure I'm in the right section. I was reading the parallel the other night to try to work out this problem I was doing, but I went and spoke with a professor, and she set me straight on the details I needed. I don't know exactly where in the book still some of those things were, but one of the parts I read earlier and did the derivations on did help later in the problem. Scattering and force field. Historically, the interest in central forces arose out of the astronomical problems of planetary motion. There is no reason, however, why central force motion must be thought of only in terms of such problems. Mention has already been made of the orbits of the Bohr atom. Let's skip that section. Another field can be investigated in terms of classical mechanics. Another field that can be investigated in terms of classical mechanics is the scattering particles by central force fields. Of course, if the particles are on the atomic scale, it must be expected that the specific results of a classical treatment would often be incorrect physically, for quantum effects are usually large in such regions. Nevertheless, many classical predictions remain valid to a good approximation. More important, the procedures for describing scattering phenomena are the same whether the mechanics is classical or quantum. We can learn to speak the language equally as well on the basis of classical physics. Okay. It's one-body formulation. A scattering problem is concerned with the scattering of particles by a central force. We consider a uniform beat of particles, whether electrons or alpha particles or planets, Whether is irrelevant. All of the same mass and energy incident upon a central force. It will be assumed that the force falls off to zero for large distances. The incident beam is characterized by specifying its intensity. Okay, also called the flux density. So I'll try drawing this, and I know there's a drawing coming up. So we'll just note everything until we get to the drawing. So we have is our central force. Oh, change my scrolling text by the way. Uniform beam of particles. We assume that the force falls off to zero for very large distances. So in other words, the distance is in the denominator. So is proportional to 1 over Rn. So that means that the farther away it goes, the smaller the force will be. The incident beam is characterized by specifying its intensity I. Okay. And there's a number of particles crossing unit area normal. It gives the number of particles crossing unit area normal to the beam at unit time. So we have the beam is going to draw the beam like so. Over to draw a box here. Have a cross section. It's the area, number of particles, A. Right. So that's I. As a particle approaches the center of force, it'll be either attracted or repelled, and its orbit will deviate from the incident straight line trajectory. After passing the center of force, the force acting on the particle will eventually diminish so that the orbit once again approaches a straight line. In general, the final direction of motion is not the same as the incident direction, and the particle is said to be scattered. The cross section for scattering in a given direction. So theta, or no, this is sigma. Not happy with, okay, I think I'm more happy with the sigma drawn this way. Sigma omega defined by, so this is the cross section for scattering. Sigma omega e omega equals dark particle scattered into a solid angle e omega per unit time. Divided by incident. I never really understood solid angle. Maybe now is a good time to look it up. Where the theta is an element of solid angle in direction omega. Why don't I look up solid angle? Try to find a good reference, and I'll share that. Okay, it's actually found a scientific paper on it. And this thing is how long? 8 pages. It's not so bad. All right, it seems good enough. So let me download this, and we'll take a look at solid angles. Published on Harvard. I do not know uh, if there is a big vetting process there. If I recall correctly, is a place where people publish papers before they really publish. So I imagine you could publish papers without them being officially published as well, like just a place to put them. I'm not sure, but I know a lot of official papers are there. So let me see, have ensured a screen in the wall. Like internet. So let me find that. Oh, I do have one up in here. Do I? Here we go. So here's the paper we'll be looking at. I'll put this right over where the book is. So I will just unshow the boom. Have it like this. All right, there we go. This is 2020. The specialized uses of solid angles mean that they are quite unfamiliar quantities. I agree with that. This article, apart from making solid angles a little more familiar, brings out several topics of general interest, such as how units are interrelated and how equations depend on the choice of units. Although the steradian is commonly used as a unit for solid angle, another unit, the square degree, is used in astronomy. Okay, I'll need that. And the unit introduced here, the solid degree, with 360 solid degrees in the hemisphere, could be used with benefits that are similar to those of the degree when it is used as a unit for a plane angle. The article, which is suitable for students at A level, introductory undergraduate level, also shows how solid angles can provide a general introduction to crystal structure, spherical trigonometry, and non-Euclidean geometry. All right. Intro, solid angle is usually given as a symbol omega. So I guess technically that's why they say it's an element of solid angle is the like dx or dy. Have a small but essential role in physics. For example, how can you characterize the intensity of a bicycle light? Its optical power, the total energy of the photons emitted per second, is clearly important, but this does not take into account the spread of the beam, which will determine the intensity in a particular direction. What is needed is a measure of the angular area of the light beam. The spread in one direction is measured as a plane angle. The spread over an area, which is what we are interested in here, is measured as a solid angle. Plane angle spread and the power of light is called radiant flux, measured in watts. That's our unit for solid angle is a steradian. And the radiant intensity is measured in watts per steradian. Sensitivity of a typical human eye is taken into account. The power is called luminous flux, expressed in lumens, and luminous intensity is given in lumens per steradian, otherwise candelas. The increasing dazzle power of bicycle lights is likely to lead to regulation limiting the luminous intensity to 200 candelas. The field of view of a human eye is around 4 steradian, so there's a steradian of a convenient size is a convenient size in this context. The field of view of the human eye is around 4 steradian. Right? Know this, we have the angle theta, we have the arc length S, we have the radius R, so S equals theta R. So using the equivalent of a steradian, this is a three-dimensional object. So we have same radius to the edge, and this is like the edge in 3D space. We have an area over the space. We're still going to the center of the sphere. No, area is three-dimensional. So it looks like this 3D area here. Is that correctly? What do you mean? So let's look. Let's see. A plane angle theta at the center of a circle of radius r with arc length s that it projects on the circumference. Okay. B, a solid angle theta at the omega at the center of a sphere of radius r with the area A that it projects on the surface of the sphere. Yeah, so it is that entire thing. Other angles are also needed when astronomers want to quantify the area of a patch of sky. They often use square degrees. A single square degree is easily visualized as a small square patch of sky where the view through a telescope will move from one corner of the square to an adjacent corner by rotating the telescope 1 degree. right? Rotate the, I got you. So what they're saying is if I'm looking at the sky and this is 1 degree, degree squared. So it's going from one corner to the other corner. This says from one corner to the other corner. So slightly less than a degree squared because it was 1 degree from edge on each edge. It'd be square root of 2, right? The sun and moon both appear as circular areas of sky with solid angle that's seen from Earth of about 0.2 degrees squared. This would be about 60 microsteradians. So in this case, the square degree is a more convenient size than the steradian. Complete equations. As discussed in Quincy and Burroughs in 2019, equations that are valid for any coherent set of units are called complete or unit invariant equations. This type of equation must be used if deductions are to be made about the dimensions of the quantities in the equation. Well, I think it's more detailed than I need. Definition of side and angle. Okay, I think I'll need this. And then we'll start with this paper. Solid angles of equal size can be very different shapes, in the same way that equal areas can be very different shapes. It is important to note that the solid angle is located in the vicinity of where the radiating lines meet, and it is a well-defined value whether or not a sphere is somehow drawn around it. In the same way, the angle between two stars as seen from Earth is well-defined, even though their distances from Earth may be unknown, making the circle and figure 1a entirely notional. The size of the solid angle is, however, most simply defined in terms of the area of a spherical surface that a solid angle will project onto a sphere centered on its apex. this 1b that we did here. And making sure I have apex down. It seems like it's at the base. Yeah, apex is the highest point, centered at its apex. It just means centered on the, uh, this definition is usually presented as solid angle equals A over R squared. So we know that looking at the arc length, theta equals S over R. So it seems to be the same thing, except now it equals S over R. Solid angle equals A over R squared. Right? It makes sense. It's like area is length times width. And then you also square the radius. The area and radius can be any coherent in any coherent unit, but the value for omega for the solid angle given by this equation is always in steradians. Okay, because basically, I guess it's technically unitless, right? We have area that's meters squared, and if radius is in meters, what we call the solid angle of a full sphere theta sphere. This equation gives the value of theta sphere to be 4 pi. I don't know how they got the 4 pi actually, which is only correct when the unit is in steradian, so the equation is not complete. Where degrees are used, the definition of steradian is 180 degrees over pi squared over AR squared, another non-complete equation. Okay, it's interesting. And steradians, degrees squared, steradian becomes 180 degrees squared over pi squared and A over R squared, another non-complete equation. The value of theta sphere in square degrees equals 360 squared over pi is about 412 1, 2, 5, 3. I know plus square degrees. How did they get 4 pi value? Guess we can put it in spherical coordinates area. Call it dA and integrate. So I did that with dA over r squared. This be dx dy over r squared. And what we have, x equals r cosine theta, y equals r sine theta, and dx equals cosine theta dr plus minus r sine theta d theta, and dy is sine theta dr plus r cosine theta d theta. So we have d omega equals cosine theta dr minus r sine theta d theta times sine theta dr plus r cosine theta d theta all over r squared. The omega equals sine theta cosine theta dr squared minus do it that way. Sine theta cosine theta dr squared plus r cosine squared theta dr d theta minus r sine theta squared dr d theta minus r squared sine theta cosine theta d theta squared. So we would have this is not the right way to do this because it looks not so good. Sine theta cosine theta dr squared minus r squared d theta squared plus dr d theta r cosine squared theta minus r sine squared theta. What throws it off is there's a minus there. How am I going to integrate this anyway? Yeah, I'm not sure how to get 4 pi. Wish you would explain that. I do need that detail, but I think this is enough for now. This close equation thing. All right, let's go back to the book. This gives us a little bit of a background on solid angle. And remember that I do offer tutoring, private tutoring, group tutoring. Let me know if you're interested. Contact me or join Discord or send me an email. Email is at the website linked above. So why don't we continue with the book? Often, sigma, omega, designated as differential scattering cross section. Central forces, there must be complete symmetry around the axis of the incident beam. With central forces, there must be complete symmetry around the axis of the incident beam. Hence, the element of a solid angle can be written I guess this image is going to show what they mean. Complete symmetry around the axis of the central beam. Right. We'll hopefully explain that. Right. For central forces, the omega equals 2 pi sine. Why is my tap not working? Let me connect it again. Sine capital theta d theta. So we'll define this as lowercase and this as capital, right? So let's go ahead and draw this thing, or maybe copy this thing. Let's see. Probably be better just to copy the image. It's just page what, 107? How to get a nice size image of this figure 319, and I'll add that to my pad, and then we'll look at it in some detail. Right? So we have this. Right? Well, capital theta is the angle between the scattered and incident directions. So we have incident direction, and this is the scattered. So theta equals scattering angle. Repulsive scattering is illustrated, so it's being pushed away. Note that the name cross section is observed in that sigma omega has the dimensions of area. Now color code this. You see big theta there for any given particle. Constants of the orbit and hence the amount of scattering are determined by its energy and angular momentum. E and L determine constant and amount of scattering. For any given particle, the constants of the orbit and hence the amount of scattering are determined by the energy and angular momentum. It is convenient to express the angular momentum in terms of the energy and a quantity known as the impact parameter. That's defined as the perpendicular distance between the center of force and the incident velocity. So S, impact parameter, the speed, so L, the angular momentum, equals mass V naught times S, which equals S square root of 2ME. The professor actually derived that more fully than the book did just now. Let's see if I can find that. Maybe I'll just start sheet that more fully. Okay. So L equals M V naught S. V naught equals E. All right. What was the reasoning behind this? The particle is coming in. E equals T plus V, which is kinetic energy plus potential energy. But the potential is coming from infinity. Infinity, V equals 0. And in this case, is a repulsive force. So if you have two positively charged particles and you put them together, you feel them push away. So they have a lot of potential. But if you pull those positively charged particles very far apart, you don't really feel them pushing against each other. So at infinity, the potential is 0. So that means that at infinity, that, so we can say V naught equals 2E over M. So this equals M over 2M2 E over M. S. So this equals square root of 2M squared E over m, or bringing the m inside the radical, still times s. So that becomes 2me times s. Right, so she did explain that more fully. And this equals L meters, kilograms, meters squared over s. Almost newtons times seconds. Newtons times meters, if I multiply by s over s. Kilograms, meters squared over seconds squared. Joules times seconds. Right, we'll leave that alone. Here's this equation 3.90. Once E and S are fixed, angle of scattering, theta, is then determined uniquely. So fixed theta equals unique when E and S are fixed. For the moment, it will be assumed that different values of S cannot lead to the same scattering angle. So S1 to theta 1, S2 theta 2, and theta 1 equals 9 theta 2. Simple enough. Therefore, the number of particles scattered into a solid angle d theta lying between theta and theta d plus d theta must be equal to the number of incident particles, the impact parameter, lying between the corresponding s and s plus ds. Right? Theta going up, d theta is the range within which the particles scatter, that spread. Impact parameter lying between the corresponding s and s plus ds. I see. So they're saying that it's not the professor was saying about how the we can assume consistent data with consistent uh, yes. So a particle comes in, if two particles come in at the same incident angle, they'll deflect in the same exact way, unlike quantum mechanics. So it's just saying that if you send an infinite number of particles at the exact same angle, you'll get that same amount scattering in the same exact way. So 2 pi L S ds equals 2 pi sigma big theta I sine big theta d theta. See if there's an equivalent of that in Professor's notes. She did mention that, but I don't remember it being written in that way. Absolute value signs are introduced in equation 3.91 because numbers of particles must, of course, always be positive, while S and big data often vary in opposite directions. If S is considered as a function of the energy, then a corresponding scattering angle, S equals S theta E. And there was an asterisk what theta is usually determined. It is at this point in the formulation that classical and quantum mechanics part company, like I was saying earlier. Indeed, it is fundamentally the characteristic of quantum mechanics that we cannot unequivocally predict the trajectory of any particular particle. We can only give probabilities for scattering in various directions. Well, in classical, we can predict exactly where. Let me get an image once more. To restart my app, starting to freeze. City. To this image when they mention it. If S is considered a function of energy and the corresponding scattering angle, the dependence of the differential cross section is on theta is given by so I think I'm going to just cancel some things here. So LSD S BS equals sigma um, sigma theta times d theta. And it looks like they're solving for sigma. So that would be sigma theta equals LS BS over theta d theta. So what's the relationship between I, L, and S again? I need to see how all of that stuff disappeared. Okay, there we go. You have to remember that L equals M V naught S equals F 2 M E. I is the number of particles crossing unit area normal in unit time. I'm not seeing where this equation comes from. The formal expression for the scattering angle. So I'm not seeing where the L, S, and I go. S is a function, theta, E. Oh, I see. So I have ds there. That's what it is. ds equals did I do it either? If whoever professor has this line here, um, yeah, sigma theta, 2 pi sine theta d theta, with no I. You divided I to the other side, 2 pi I s ds. Maybe that's where my I have that right. She has 2 I's. That's where my people look and confirm. This page, what, 107? Yeah, these are I's, not L's. So I need this, but that means that this will cancel, this will cancel, this will cancel, this will cancel. So that means that this I won't be here because that will have canceled. And this L won't be here because that will have canceled. We'll be left with this SD theta equals sigma big theta sine theta d theta. And then if I was solving for sigma theta equals S bs over sine theta d theta sigma big theta equals, and now I think we have what they have, S over sine theta, and ds over d theta. Formal expression for the scattering angle, big theta. Oh, and by the way, this was an important formula that my professor highlighted. The formal expression for the scattering angle big theta as a function of s can be directly obtained from the orbit equation, equation 3.36. So theta equals r naught r the r squared square root 2m. This is one of the equations I went through yesterday, looking over, trying to figure out that problem. So what that symbol is, that's 1 over r squared. Plus theta naught equals 1 over r. I hate this abbreviation product because I don't really understand applying that. So I had difficulty applying it the other day. And get theta again, for simplicity, we will consider the case of purely repulsive scattering, as the orbit must be symmetric about the direction of the periapsis. The scattering angle is given by theta equals pi minus 2 psi. We have this angle here equal these, which makes sense. This is 394. Phi is the angle between the direction of the incoming asymptote and the periapsis closest approaching direction. Seems to me that this angle here would be a right angle. To keep it as a box. Angle between the closest approach and the original angle of incidence is psi. In turn, psi can be obtained from equation 3.36. The useful equation. By setting r naught equals 0. So can be gotten from 3.36, given that r naught is infinity, theta naught is pi, that's the incoming direction, and theta equals pi. And you notice this mine is one psi, and r equals r. You know, from 3.36, setting r naught to infinity, theta naught to pi, theta equals pi minus psi, coming from infinity. Angle. This means it's a direct hit. Theta is pi minus psi. It bounces straight back. This means direct hit. The distance, the distance of closest approach. A trivial rearrangement then leads to psi equals Rm to infinity of dr over r squared square root 2me over l squared 2mv over l squared minus over r squared. It's 3.95. Glad they wrote that one out for us. Expressing L in terms of the impact parameter S, equation 3.90. So I wrote that down. Keep that one. The resultant expression for big data S is I minus 2 integral infinity S dr over r squared v minus S squared, and this is 3.96. The dreaded r equals 1 over u. Differently, theta S equals pi minus 2, 0 to um s du over square root 1 minus v u over e minus s squared u squared. This is 3.97. All right. Which we have here. Actually need to take a break. So I may not finish this today after all. Let me come back tomorrow or later. What time is it? 11? I'll see. So probably will be back on tomorrow. But I may come back sooner. And those who check it out later, be sure to like and subscribe if you haven't. Put this book up here. And help me get to 1,000 subscribers. Let me know if you need any tutoring. And I'll be back tomorrow for sure, if not later today. And we'll see about finishing this section, as well as which is it we'll cover in the on Wednesday. So Wednesday is the next class in that class. And hit the wrong button there. So I'm sure we're not going to talk about the three-body problem yet. So, right. Thank you all for watching. Those who joined, I'll see you all next time.